The morning of March 7th, 1942, found Boeing's Plant 2 in Seattle, operating under impossible mathematics. Production manager Harold Emmons stood on the factory floor watching teams of riveters swarm over a B-17 Flying Fortress wing section, and the calculations running through his mind pointed toward catastrophe. Current assembly rates, each bomber wing required approximately 20 hours of labor from start to finish. The Army Air Forces had just doubled their aircraft orders. Again, the numbers didn't merely fail to add up, they represented a physical impossibility. Emmons wasn't alone in his anxiety that morning. Across America's aviation industry, production supervisors faced the same brutal arithmetic. President Roosevelt had declared that the United States would produce 50,000 aircraft in 1942 alone. The announcement, meant to inspire confidence among allies and strike fear into Axis hearts, had instead created near panic among the engineers and managers who understood what those numbers actually demanded. Building 50,000 aircraft meant building 100,000 wings, perhaps more, accounting for training aircraft, replacements, and combat losses. The existing manufacturing processes, refined through decades of careful craftsmanship, could not possibly scale to meet such requirements. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The B-17 Flying Fortress represented American strategic bombing doctrine, made manifest in aluminum and steel. Its 4 Wright Cyclone engines could carry the aircraft and a crew of 10 across hostile airspace to targets deep in enemy territory. Its defensive armament, 1350 caliber machine guns in the later variants, created overlapping fields of fire that gave the bomber its fortress nickname. But before any B-17 could strike German industry or Japanese shipping, someone had to build it, and the wings, those massive structures spanning 103 feet from tip to tip, represented perhaps the most challenging component to manufacture at scale. Traditional aircraft construction, inherited from the industry's barnstorming origins, treated each plane as a semi-custom creation. Skilled craftsmen worked from detailed drawings, hand-fitting components, adjusting tolerances, solving problems through experience and intuition. A master riveter might spend an entire career perfecting the technique of driving aluminum rivets without damaging surrounding structure. Assembling a bomber wing required orchestrating dozens of such specialists, each performing tasks that couldn't easily be standardized or accelerated. The Boeing plant, where Emmons wrestled with production mathematics, had been constructed specifically to manufacture B-17s at unprecedented volume. The facility stretched across acres of Seattle real estate, its roof designed to camouflage the factory from potential Japanese air attack following Pearl Harbor. Inside, assembly lines moved partially completed bombers through sequential stations where teams installed specific systems and components. The process worked after a fashion, but it worked slowly, far too slowly for what the war demanded. Boeing wasn't merely competing against other American manufacturers. The company faced a far more ominous competitor: time itself. Every day, production lagged behind demand, represented another day that American bomber crews flew worn-out aircraft, another day that Allied air superiority remained uncertain, another day that the outcome of the war hung in balance. German industry, operating under Albert Speer's rationalization programs, was increasing its own aircraft production with alarming efficiency. American factories had to do more than match German output. They had to overwhelm it. Into this pressure cooker of impossible demands and desperate urgency walked individuals whose names history would largely forget. Men and women who came to aircraft factories with no prior aviation experience, no engineering degrees, no formal qualifications, beyond willingness to learn and determination to contribute. The war's democratic leveling had thrust factory gates open to workers who in peacetime would never have approached skilled manufacturing. Among them walked solutions to problems that experts insisted had no solutions. March of 1942 marked the sixth month of American participation in World War II following the December 7, 1941 attack on Pearl Harbor. The war news offered little encouragement. Japanese forces had conquered the Philippines, captured Singapore, overrun the Dutch East Indies, and threatened Australia itself. In Europe, German armies controlled territory from the Atlantic coast to the outskirts of Moscow. American forces had yet to engage in significant ground combat, but the nation's industrial capacity represented the one advantage that might eventually tip the balance. Aircraft production embodied this industrial struggle with particular intensity. Bombers, especially strategic bombers, capable of carrying the war to enemy homelands, would determine whether the Allies could strike back effectively or merely defend against Axis advances. The B-17, originally designed in the mid-1930s as a coastal defense weapon, had evolved into America's primary heavy bomber. Its production rate would directly influence Allied capabilities in every theater of operation. The specific bottleneck that consumed Harold Emmons' attention that March morning involved wing spar assembly. The wing spar, essentially a massive beam running the length of each wing, provided the primary structural support for the entire wing assembly. It carried flight loads, supported the engines, housed fuel tanks, and formed the foundation upon which everything else attached. Building a wing spar required precision measured in thousandths of an inch, despite the structure's enormous size and complexity. Traditional wing spar construction involved assembling multiple sections, each requiring hundreds of rivets driven by hand. Teams of riveters worked from both sides of the spar simultaneously. One worker held a bucking bar against the rivet's tail, while another drove the rivet head with a pneumatic hammer. The process demanded perfect coordination, exact positioning, and consistent force. Too little pressure, and the rivet failed to form properly, creating a weak joint that might fail catastrophically during flight. Too much pressure, and the rivet crushed, damaging the surrounding aluminum structure. Master riveters developed almost supernatural sensitivity to their tools. They could hear in the rivet gun's sound whether they were achieving proper compression. They could feel in the bucking bar's vibration whether the rivet was forming correctly. This knowledge came through years of experience, through countless repetitions that developed muscle memory and intuitive understanding. You couldn't teach it in a classroom. You couldn't write it in a manual. An apprentice riveter might require 6 months to develop basic competence and years to achieve true mastery. The mathematics of scaling this craft-based process to industrial volume didn't work. Boeing employed thousands of workers in Seattle, but skilled riveters remained in desperately short supply. The company had implemented training programs, recruited experienced workers from other industries, even convinced some retirees to return to factory work. Still, the shortage persisted, and even if Boeing somehow found sufficient skilled workers, the fundamental process remained too slow. 20 hours per wing meant that even running 3 shifts around the clock, a single wing assembly station could produce only slightly more than 3 complete wing sets weekly. The pressure manifested in multiple directions simultaneously. Military procurement officers visited the plant regularly, questioning production managers about delivery schedules and capacity projections. Boeing's senior leadership demanded improvements, offering support, but ultimately unable to change the physical limitations of existing processes. Workers themselves felt the urgency, understanding that pilots were dying while waiting for aircraft that factories couldn't build fast enough. The weight of that knowledge wore on everyone. Other aircraft manufacturers faced identical challenges. Consolidated Aircraft in San Diego produced B-24 Liberators using similar construction techniques. Douglas Aircraft built various bomber types with comparable methods. Across the industry, engineers sought solutions. Some companies experimented with different rivet patterns, attempting to reduce the number of fasteners required. Others tried reorganizing work teams, searching for more efficient labor allocation. A few pioneered new tools, developing rivet guns with better ergonomics or improved power delivery. These incremental improvements helped. Production rates crept upward as factories learned and adapted, but incremental improvements wouldn't meet exponential demand increases. The situation required not optimization, but transformation. Something had to change, fundamentally, about how bomber wings got assembled. The question that nobody could answer was what that change might look like and where it might come from. The Boeing plant's employment records from early 1942 reveal the massive influx of new workers hired to support increased production. In January alone, the Seattle facility added over 800 employees. They came from extraordinarily diverse backgrounds. Former loggers, accustomed to dangerous physical work, found themselves operating drill presses and rivet guns. Farm workers who had never seen an aircraft up close studied technical drawings of bomber components. Women who had worked in canneries or textile mills assembled electrical systems and control surfaces. This rapid expansion created its own challenges beyond the obvious training requirements. Experienced workers suddenly found themselves supervising teams of complete novices. Foremen, accustomed to managing small groups of skilled craftsmen, now oversaw dozens of semi-trained workers learning on the job. Quality control became simultaneously more critical and more difficult. Every worker mistake, every improperly driven rivet, every misaligned component threatened to create a defect that might not be discovered until catastrophic failure killed a crew. Against this backdrop of expansion, urgency, and barely controlled chaos, Janet Morrison arrived for her first day at Boeing's Plant 2. She was 26 years old, stood 5 feet 3 inches tall, and weighed perhaps 110 pounds. Before the war, she had worked as a seamstress in a downtown Seattle dress shop, creating custom garments for wealthy clients. She had no mechanical experience, no technical training, and no particular reason to believe she could contribute to aircraft manufacturing. But the war needed workers. Boeing was hiring, and the pay exceeded anything available in peacetime dress shops. Morrison's hiring interview, conducted by a harried personnel manager processing dozens of applications daily, lasted perhaps 15 minutes. Could she follow written instructions? Yes. Did she mind working with loud machinery? She could manage. Could she work any shift, including nights and weekends, whatever was needed? She was hired immediately and told to report for training the following Monday. The training program Morrison entered reflected Boeing's desperate attempt to transform untrained civilians into aircraft workers in weeks rather than years. Instructors, themselves often recent hires who had shown aptitude and advanced quickly, taught basic skills: how to read technical drawings, how to identify different fastener types, how to operate pneumatic tools safely, how to recognize quality problems. The curriculum covered enormous ground, rapidly, inevitably sacrificing depth for breadth. Morrison discovered that her seamstress background provided unexpected advantages. She understood how tension in one area affected structure elsewhere, a principle that applied to fabric and aluminum alike. She grasped how patterns transferred from paper to physical material, whether cloth or metal. Her fingers, trained to manipulate needle and thread with precision, adapted readily to handling small components and fasteners. The transition from custom dressmaking to aircraft assembly, seemingly absurd, proved more natural than anyone, including Morrison herself, had anticipated. After 2 weeks of classroom instruction and supervised practice, Morrison received her assignment at riveting crew, wing assembly section, second shift. She would work from 4 in the afternoon until midnight, 6 days weekly, with overtime available and often mandatory. Her starting wage was 90 cents per hour, nearly double what she had earned as a seamstress. For that compensation, she would help build the wings that carried American bombers into combat. Her first evening on the production floor was overwhelming. The noise level was staggering. Hundreds of pneumatic tools hammering simultaneously, metal striking metal in constant percussion. The scale was immense. Bomber wings, larger than some houses, stretched across assembly jigs. The complexity was daunting. Technical drawings showing thousands of individual parts that somehow had to fit together with perfect precision. Morrison stood beside her supervisor, a grizzled veteran riveter named Frank Kowalski, and wondered if she had made a terrible mistake. Kowalski had worked aircraft manufacturing since the 1920s, learning his trade when every plane was essentially handmade. He possessed the deep knowledge and intuitive understanding that years of practice created. He could examine a rivet joint and immediately identify whether it had been properly formed. He could listen to a rivet gun and diagnose problems from the sound alone. He represented exactly the kind of skilled craftsman that factories desperately needed and couldn't find enough of. What Kowalski saw when he looked at Janet Morrison was a small woman with no obvious qualifications for heavy industrial work. What Morrison saw when she looked at the wing assembly process was something nobody had expected. She saw inefficiency. She saw wasted motion. She saw workers getting in each other's way. She saw a process that, for all its technical sophistication, operated with surprising chaos. Morrison said nothing that first shift. She watched. She listened. She learned. Kowalski assigned her to relatively simple tasks, driving rivets in easily accessible locations where mistakes would be obvious and correctable. She performed adequately, neither impressive nor incompetent, just another new worker learning the job. But inside her mind, observations were accumulating, connections were forming. An idea was beginning to take shape that would transform not just Boeing's wing assembly process, but American bomber production across the entire aviation industry. The specific problem that captured Morrison's attention involved what experienced workers called the reach problem. Wing spar assembly required riveters to work from both sides of the structure simultaneously. In many locations, particularly where spars intersected with ribs and other internal structures, the space available for positioning workers and tools was severely limited. Riveters had to reach into cramped spaces, contort their bodies into awkward positions, and work effectively despite terrible ergonomics. This physical challenge explained partly why skilled workers remained so valuable. Experienced riveters had learned through trial and error which positions worked, how to brace themselves for maximum force application, how to manipulate tools in confined spaces. They had developed the physical strength and flexibility required for sustained work in difficult positions. New workers struggled constantly, unable to access locations properly or maintain the consistent force application that proper riveting required. Morrison observed that the reach problem resulted directly from the assembly sequence Boeing used. Workers installed internal wing structures first, building from the inside out. This sequence made structural sense from an engineering perspective. Load-bearing components went in early, forming the foundation for everything that followed. But it created enormous problems for the workers who had to install subsequent components in increasingly confined spaces. What if, Morrison wondered, the sequence was reversed? What if external structures went in first, leaving internal spaces open and accessible? Workers could reach everything easily. They could position themselves comfortably. They could see what they were doing. The physical challenges that limited productivity would simply disappear. The idea seemed obvious once she thought of it. Too obvious, surely. The engineers who designed the assembly process had considered such a basic alternative. Surely there were compelling reasons why the current sequence was necessary. Morrison was a former seamstress with 2 weeks of training. The probability that she had identified a fundamental improvement that Boeing's experienced engineers had overlooked seemed vanishingly small. Still, the thought nagged at her through the remaining hours of her first shift. As she watched workers struggle to access difficult locations, as she saw time wasted repositioning tools and bodies, as she experienced firsthand the physical strain of working in cramped spaces, the idea refused to go away. Maybe it was foolish. Maybe she didn't understand some crucial technical constraint, but maybe just possibly. Fresh eyes had seen something that familiar eyes had stopped noticing. Morrison's second shift passed much like her first. She worked, she watched, she thought. By her third evening on the production floor, she had convinced herself that her idea at least deserved consideration. The question was whether anyone would listen to a new hire suggesting that Boeing's entire wing assembly process should be redesigned. The opportunity came unexpectedly during a shift break. Morrison found herself standing near Harold Emmons, the production manager she had seen but never met. Emmons was examining a partially completed wing, his expression troubled. He was clearly wrestling with some problem, and his body language suggested frustration bordering on despair. Morrison later recalled that she almost walked away. Speaking to a senior manager was presumptuous for a new worker, suggesting process improvements after 3 days on the job bordered on arrogant. But she thought about pilots waiting for aircraft. She thought about the war that needed winning. She stepped forward. "Excuse me, sir," she said quietly. "May I ask a question about the assembly sequence?" Emmons turned, surprised to be addressed by a worker he didn't recognize. His initial expression suggested irritation at the interruption. But something in Morrison's manner, perhaps the evident nervousness that indicated she understood she was overstepping, made him pause. "What's your question?" he asked. Morrison took a breath and explained her observation. The reach problem slowed production because the assembly sequence created confined spaces where workers struggled to operate effectively. What if they reversed the sequence, building from outside in rather than inside out? Workers could access everything easily, productivity would increase, and training new workers would become simpler because the physical demands would decrease. Emmons listened without interrupting. His expression shifted from irritation to attention to something Morrison couldn't quite read. When she finished, he was quiet for several seconds. "What's your name?" he finally asked. "Janet Morrison, sir. I started Monday." "Monday, 3 days ago." "Yes, sir." Emmons looked at the wing, then back at Morrison. "Do you understand why we assemble inside out? The structural loads, the engineering requirements?" Morrison admitted she didn't fully understand the engineering. She only understood what she observed. The current process created difficulties that seemed potentially avoidable. Emmons studied her for another moment, then did something that surprised everyone within earshot. He called over his chief engineer, a man named Robert Hayes, and asked Morrison to repeat her suggestion. Hayes's initial reaction was skeptical. The assembly sequence had been carefully designed by experienced engineers. Structural requirements dictated the order. Load paths needed to be established before other components could be installed. The suggestion, while creative, demonstrated a novice's misunderstanding of technical constraints. But Emmons pressed. "Humor me," he said to Hayes. "Is there any structural reason, any engineering requirement that absolutely mandates the current sequence?" Hayes thought about it. The honest answer, he finally admitted, was no. The sequence followed convention and seemed logical, but no fundamental engineering principle demanded it. In theory, the order could be reversed. The question was whether doing so would create other problems. "Work it up," Emmons said. "Take one wing. Try it Morrison's way. See what happens." What happened over the next 2 weeks would begin the transformation of American bomber production. Hayes and his engineering team designed a modified assembly sequence following Morrison's basic concept. Instead of installing the internal wing spar structure first, they would position external skin panels and major structural components first, leaving the interior completely accessible. Internal components would be installed last, through large access openings that would be closed only after all interior work was complete. The modified process required redesigning assembly jigs, retraining work crews, and revising hundreds of pages of technical instructions. Hayes's team worked around the clock, driven by Emmons's insistence that the trial receive immediate priority. Boeing's corporate leadership, initially skeptical, grudgingly approved the experiment after Emmons explained the potential productivity gains. The first wing assembled using Morrison's reversed sequence took 18 hours from start to finish instead of the usual 20. Not a dramatic improvement, but promising. More significantly, the workers involved reported that the process felt dramatically easier. They could see what they were doing. They could position themselves comfortably. They spent less time maneuvering tools into confined spaces, and more time actually installing fasteners. The second wing took 16 hours. The third took 14. As workers gained familiarity with the modified sequence and engineers refined the process, productivity continued improving. Quality control inspections revealed no increase in defects. In fact, defect rates decreased slightly because workers could inspect their own work more easily during assembly. By the end of March 1942, Boeing's wing assembly process had been fundamentally transformed. What had required 20 hours now took 12, and engineers believed further improvements were possible. The production bottleneck that Harold Emmons had considered insurmountable had been broken by a former seamstress with less than a month of aircraft manufacturing experience. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Morrison's innovation spread rapidly through Boeing's organization and beyond. Other assembly sections adopted similar reversed sequence approaches. Components that had traditionally been installed early in the build process were repositioned later, keeping work areas open and accessible. The cumulative effect of these changes was revolutionary. By April of 1942, Boeing's Seattle plant was assembling B-17 wings faster than any aviation facility in the world. The improvement came not from new machinery or increased workforce, but from Janet Morrison's fundamental rethinking of the assembly sequence. Word spread quickly through the American aviation industry. If Boeing could cut wing assembly time nearly in half through process innovation, what other bottlenecks might yield to fresh thinking? The War Production Board, established by President Roosevelt in January 1942 to coordinate industrial mobilization, took immediate interest. Officials recognized that Morrison's innovation represented exactly the kind of productivity breakthrough that mass production demanded. Traditional craft-based manufacturing, however refined, could not scale to wartime requirements. The nation needed new approaches that emphasized efficiency over tradition. William Knudsen, who had left his position as president of General Motors to lead defense production efforts, visited Boeing's Seattle facility in late April. He spent an entire day observing the modified wing assembly process, asking detailed questions about implementation challenges and productivity gains. According to records preserved at the National Archives, Knudsen immediately grasped the innovation's broader implications. The meeting between Knudsen and Morrison, which occurred in Harold Emmons' office, illustrated the war's democratizing effect on American industry. Here sat one of the nation's most powerful industrialists, a man who had built General Motors into a manufacturing colossus, earnestly soliciting advice from a former seamstress who had worked in aircraft manufacturing for 6 weeks. And Knudsen asked Morrison to explain her thinking process. How had she identified the problem? What made her believe reversal would work? How might similar thinking apply to other manufacturing challenges? Morrison's answers revealed an intuitive understanding of workflow efficiency that formal engineering education sometimes obscured. She explained that her seamstress background had trained her to think about sequence and access. When creating a complex garment, you had to consider which seams could be sewn when, which components needed installation before others, how to maintain access to areas requiring detailed work. Aircraft assembly, she suggested, involved similar considerations, despite the vastly different scale and materials. Knudsen left Seattle convinced that American industry needed more Janet Morrisons, workers with fresh perspectives, unburdened by assumptions about how things had always been done. He directed the War Production Board to circulate Boeing's assembly innovations throughout the aviation industry and to actively solicit process improvements from production workers, regardless of their formal qualifications or seniority. The directive produced remarkable results. At Consolidated Aircraft in San Diego, a former furniture maker named Thomas Chen suggested reorganizing B-24 Liberator fuselage assembly. His woodworking background gave him insights into structural support and bracing that metal workers had approached differently. Chen's modifications reduced fuselage assembly time by 18% while actually improving structural integrity. At Douglas Aircraft in Long Beach, a woman named Marie Rodriguez, who had worked in automotive upholstery before the war, revolutionized the installation of bomber interior components. She recognized that fabric installation techniques from automobile seats could be adapted for aircraft insulation and soundproofing. Her methods cut installation time in half and improved quality consistency. These innovations shared common characteristics. They came from workers with non-traditional backgrounds who brought different mental frameworks to manufacturing problems. They focused on process rather than technology, achieving improvements through reorganization rather than new equipment, and they demonstrated that expertise developed in seemingly unrelated fields could transfer productively to aircraft manufacturing when workers were empowered to contribute ideas. The cultural shift within aviation plants was profound. Traditionally, hierarchical organizations, where engineers designed processes and workers executed them, began embracing suggestions from the factory floor. Companies established formal programs for collecting and evaluating worker innovations. Some plants created incentive systems, offering monetary bonuses for implemented suggestions. Others simply created mechanisms for ideas to reach decision-makers who could authorize changes. Boeing expanded Morrison's role significantly. By summer 1942, she had been promoted to process analyst, a newly created position that involved studying assembly operations and recommending improvements. Her lack of formal engineering credentials initially created resistance from some technical staff, but her track record of successful innovations overcame skepticism. She worked closely with engineering teams, providing observations about practical manufacturing challenges, while engineers handled technical implementation details. One of Morrison's subsequent innovations addressed rivet gun ergonomics. She noticed that the standard pneumatic rivet guns, designed decades earlier for male workers, were poorly suited for smaller-statured operators. Many women working in aircraft plants struggled with tools that were too heavy, too large for their hands, and awkward to manipulate. Morrison collaborated with tool manufacturers to develop lighter rivet guns with better weight distribution and handles sized for smaller grips. The modified tools improved productivity for all workers, not just women. Men found the lighter guns less fatiguing during extended shifts. The better ergonomics reduced repetitive stress injuries across the workforce. This represented another pattern in wartime manufacturing innovation. Changes implemented to accommodate previously excluded workers often benefited everyone, revealing that standard designs had actually been optimized for only a subset of potential operators. The statistical impact of Morrison's wing assembly innovation became clear through production records compiled by the War Production Board. Boeing's Seattle plant, which had produced 37 complete B-17s in March 1942, manufactured 54 in April and 68 in May. The increases came without expanding the workforce or adding factory space. Assembly time reductions created capacity that translated directly into additional aircraft. Other manufacturers implementing similar process improvements showed comparable gains. Consolidated's B-24 production increased by 42% in the 3 months following Chen's fuselage assembly innovations. Douglas boosted output by 36% after adopting Rodriguez's interior installation methods. Across the American aviation industry, production curves that had been rising steadily began climbing exponentially. The numbers told a remarkable story. American factories produced approximately 6,000 military aircraft in 1941, the year before Pearl Harbor. In 1942, production reached nearly 48,000 aircraft. The 1943 total exceeded 86,000. These increases resulted from multiple factors, including factory expansion, workforce growth, and improved supply chains. But process innovations contributed substantially, squeezing more productivity from existing resources. The B-17 specifically exemplified this production acceleration. Boeing, Douglas, and Lockheed Vega together manufactured over 6,000 B-17s in 1943 alone, more than triple the prior year's production. These bombers, emerging from assembly lines at unprecedented rates, filled the ranks of the 8th Air Force in England and other units across multiple theaters. They conducted the strategic bombing campaign that systematically destroyed German industrial capacity. The human cost of this industrial achievement deserves acknowledgement. Workers maintaining the brutal pace of wartime production endured extraordinary physical and psychological stress. 12-hour shifts, 6 or 7 days weekly, became standard in many plants. Fatigue-related accidents increased despite safety programs. Families strained under the burden of absent parents working around-the-clock schedules. The social disruption of rapid industrial mobilization affected millions of American families. Janet Morrison herself exemplified these pressures. Her promotion to process analyst brought increased responsibility and longer hours. She typically worked 60 to 70 hours weekly, analyzing assembly operations, documenting improvement opportunities, and coordinating with engineering teams. Her personal life essentially disappeared, consumed by work demands. She later described this period as simultaneously the most fulfilling and most exhausting of her life. The gender dynamics within aircraft plants evolved significantly during this period. Women constituted approximately 4% of aviation industry workers in 1941. By 1943, that figure exceeded 30% in many facilities. Some plants, particularly those manufacturing smaller components, employed female majorities. This demographic transformation occurred despite widespread skepticism about women's capabilities in technical manufacturing. Morrison's prominence as an innovator helped challenge these prejudices, though progress was uneven. Some male workers and managers enthusiastically embraced female colleagues' contributions. Others resisted, maintaining that women's wartime employment was temporary necessity rather than permanent change. The tension between these perspectives created complicated workplace dynamics that affected daily operations. The technical challenges of scaling B-17 production extended far beyond wing assembly. Every aircraft component presented manufacturing bottlenecks that required systematic attention. Engine production, for instance, demanded precision machining of thousands of parts that had to function together with perfect reliability. Electrical systems required miles of wiring installed according to complex specifications. Hydraulic components needed assembly by workers who understood fluid dynamics and pressure systems. The Wright Cyclone engines that powered B-17s represented particular manufacturing challenges. Each 9-cylinder radial engine contained approximately 10,000 individual parts. Tolerances were measured in 10,000ths of an inch. Assembly required specialized knowledge and equipment. Wright Aeronautical's engine plants in New Jersey operated continuously, producing Cyclones at rates that would have seemed impossible before the war. The integration of components manufactured at disparate facilities created logistical complexities that required unprecedented coordination. Boeing's Seattle plant assembled B-17s using wings manufactured in-house, engines from Wright in New Jersey, propellers from Curtiss in Ohio, instruments from Colesman in New York, and hundreds of other components from suppliers across the nation. Every part had to arrive on schedule, meet exact specifications, and install properly. Supply chain disruptions could halt production instantly. The Army Air Forces maintained rigorous quality standards despite production pressures. Every completed bomber underwent extensive testing before acceptance. Engines were run through complete power cycles. Control surfaces were tested through full range of motion. Electrical systems were energized and checked. Hydraulic systems were pressurized and inspected for leaks. Any deficiency resulted in rejection, forcing factories to identify and correct problems. These quality requirements created tension between production goals and manufacturing reality. Plant managers pressed for speed while inspectors insisted on perfection. The conflict was never fully resolved, representing an inherent challenge of mass production. Factories sought efficiency while inspectors demanded reliability. Both imperatives were legitimate. Both were necessary. Managing the balance required constant negotiation. Morrison's innovations influenced this balance by improving first-time quality rates. When assembly processes were well designed, workers could execute them correctly, more consistently. The reversed wing assembly sequence, by providing better access and visibility, reduced errors that required rework. Fewer defects meant less time spent on corrections, which translated into genuine productivity improvements rather than merely faster production of defective equipment. By autumn 1943, Boeing was assembling B-17s at rates that would have seemed like fantasy 18 months earlier. The Seattle plant alone produced over 300 bombers monthly. Douglas's Long Beach facility contributed additional units. Lockheed Vega's Burbank plant assembled still more. The combined output equipped dozens of bomb groups that were systematically reducing German industrial capacity through round-the-clock strategic bombing. The bombers, rolling off assembly lines, carried the labor of hundreds of thousands of American workers. Each B-17 represented approximately 160,000 labor hours distributed across primary manufacturers and component suppliers. Morrison's contribution to reducing wing assembly time, saved perhaps 6 hours per aircraft, multiplied across thousands of bombers. Those savings represented hundreds of thousands of hours of additional productive capacity. The strategic impact became measurable through combat operations. The 8th Air Force in England, which began operations in summer 1942 with barely sufficient aircraft for token missions, grew into the largest air force in history. By summer 1944, the 8th regularly dispatched over 1,000 bombers on single missions. This overwhelming numerical superiority came directly from American industrial capacity, from factories that had learned to build complex aircraft at mass production rates. The Schweinfurt-Regensburg mission of August 17, 1943, illustrated both the power and limitations of strategic bombing. Over 300 B-17s struck ball-bearing factories and aircraft plants deep in Germany. The attacks damaged critical industrial facilities, but cost the 8th Air Force 60 aircraft and 600 crewmen. The losses demonstrated that even with numerical superiority, unescorted daylight bombing remained desperately dangerous. The solution came through combining bomber production with long-range fighter development. The P-51 Mustang, equipped with external fuel tanks that extended its range dramatically, began escorting bombers deep into Germany in early 1944. The combination of mass-produced bombers and long-range fighters achieved the air superiority that strategic bombing doctrine required. German fighter forces, facing overwhelming numbers and increasingly effective opposition, were gradually destroyed through sustained attrition. Morrison witnessed these strategic developments through production statistics and news reports rather than direct experience. Her war was fought on factory floors in Seattle, measuring efficiency in hours saved per aircraft rather than missions flown or targets destroyed. Yet she understood the connection between her work and combat outcomes. Every hour saved in wing assembly meant additional aircraft available sooner. Every bomber delivered early potentially saved lives by shortening the war. The personal toll on Morrison and millions of workers like her accumulated gradually. Chronic exhaustion became normalized. Most workers operated continuously on inadequate sleep, sustained by coffee, cigarettes, and sheer determination. Minor injuries were ignored unless they prevented work. Stress manifested in various ways: irritability, difficulty concentrating, stress-related health problems. The culture discouraged complaints. Everyone understood the stakes. Morrison's relationship with Frank Kowalski, the veteran riveter who had supervised her initial training, evolved into genuine friendship despite their different backgrounds and perspectives. Kowalski represented the old craft tradition, knowledge gained through decades of experience. Morrison represented the new production engineering approach, efficiency through systematic analysis. Their conversations revealed fundamental tensions within industrial transformation. Kowalski worried that the emphasis on speed and standardization was eliminating craftsmanship. He had spent his career developing skills that mass production was rendering obsolete. The new processes Morrison championed allowed semi-trained workers to achieve results that previously required master craftsmen. Kowalski understood the necessity, but mourned the loss of something he valued deeply. Morrison sympathized, but believed the transformation was inevitable and necessary. The war demanded production volumes that traditional methods couldn't achieve. Industrial democracy, allowing ordinary workers to contribute their talents, was unlocking productive capacity that peacetime hierarchies had suppressed. The future belonged to systems that empowered people rather than traditions that restricted them to predefined roles. Their debates, conducted during lunch breaks and shift changes, reflected broader societal questions about industrial modernity, skill and expertise, hierarchy and democracy. The war had accelerated transformations that might otherwise have unfolded over decades. Morrison and Kowalski, friend and mentor despite their disagreements, personally experienced history's pivot point. January 1944 witnessed the culmination of Morrison's impact on B-17 production. Boeing's Seattle plant achieved the unprecedented rate of 362 bombers delivered in a single month. The entire B-17 program, encompassing Boeing, Douglas, and Vega production, exceeded 500 units monthly. These numbers represented the maturation of mass production techniques applied to complex military aircraft. The achievement came with costs beyond worker fatigue and social disruption. The emphasis on quantity sometimes compromised refinement. Late-model B-17s incorporated continuous improvements based on combat experience, but production pressures limited how quickly changes could be implemented. Some known issues persisted in delivered aircraft because correcting them would have disrupted assembly lines. Quality metrics revealed this tension. The rejection rate for completed bombers, while never high, had increased slightly as production accelerated. Most rejected aircraft had minor deficiencies that required only brief additional work before acceptance. Catastrophic failures were rare, testament to effective quality control despite production pressures. Still, the statistics indicated that absolute quality had been subordinated slightly to productive quantity. Morrison wrestled with this compromise. Her innovations had contributed to production acceleration, but was speed being prioritized excessively? Were some quality problems traceable to insufficient attention during assembly? The questions troubled her, particularly when she learned of bomber losses that might have resulted from manufacturing defects. The connection between her factory work and combat deaths became uncomfortably direct. The Army Air Force's investigation of a B-17 that crashed during training in March 1944 intensified Morrison's concerns. The accident killed 10 crewmen. Initial findings suggested that a wing spar failure had caused the crash. If manufacturing defects were responsible, Morrison's modified assembly process might have contributed. She demanded access to the investigation, determined to understand what had happened. The investigation ultimately determined that the crash resulted from material failure unrelated to assembly procedures. The wing spar had been manufactured from aluminum alloy that had been improperly heat-treated by the supplier, creating internal weaknesses that catastrophic stress revealed. Morrison's assembly process was exonerated, but the incident reminded her that manufacturing decisions had life-and-death consequences. The emotional burden of this responsibility affected Morrison profoundly. She began having nightmares about bomber crashes, about crews dying because of manufacturing defects she might have prevented. The stress manifested physically through weight loss, insomnia, and stress-related health problems. Her supervisors, recognizing signs of burnout, insisted she take a week of leave. She resisted, but eventually complied. The rest period provided perspective. Morrison recognized that she had been driving herself unsustainably, as had millions of other war workers. The pressure to produce, the knowledge that delays meant deaths, the constant emergency that had lasted years, all created psychological strain that had to be managed rather than ignored. She returned to work with renewed commitment, but also greater awareness of personal limitations. By summer 1944, Allied forces had landed in Normandy and were advancing across France. The strategic bombing campaign had devastated German industry. The outcome of the war in Europe, while not yet certain, clearly favored the Allies. Production pressures began easing slightly as accumulated aircraft inventory provided some cushion against immediate demand. Morrison used this breathing space to implement additional refinements to wing assembly processes. Her focus shifted toward quality improvements rather than pure speed increases. She worked with engineering teams to develop enhanced inspection procedures that could be integrated into assembly workflows without significantly impacting production rates. The goal was maintaining high output while ensuring maximum reliability. One innovation from this period involved what Morrison called progressive inspection. Rather than conducting quality checks only after assembly completion, inspectors would examine work continuously during assembly. Problems could be identified and corrected immediately rather than requiring extensive rework after discovery during final inspection. The approach required reorganizing inspection personnel and revising procedures, but testing showed significant quality improvements. The progressive inspection system reduced the final rejection rate by approximately 40% while actually decreasing total inspection time. Problems caught early were easier to fix than defects discovered after subsequent assembly steps had been completed. The innovation demonstrated again that thoughtful process design could simultaneously improve quality and efficiency, rather than forcing trade-offs between them. Boeing adopted progressive inspection across its operations, and other manufacturers followed. The War Production Board disseminated technical bulletins describing the system, and aviation plants nationwide began implementation. This represented the mature phase of wartime production innovation. The desperate improvisations of 1942 had evolved into systematic, continuous improvement by 1944. The final statistics of B-17 production revealed the magnitude of American industrial achievement. Between 1939 and 1945, Boeing, Douglas, and Lockheed Vega manufactured approximately 12,700 B-17s of all variants. The aircraft equipped 33 bomb groups in Europe alone, plus additional units in other theaters. They dropped approximately 640,000 tons of bombs on Axis targets, more than any other American aircraft type. Morrison's contribution to this achievement, while impossible to quantify precisely, was substantial. Her wing assembly innovation reduced manufacturing time significantly across thousands of aircraft. Her subsequent process improvements enhanced quality and efficiency throughout Boeing's operations. Her example, demonstrating that fresh perspectives could revolutionize established practices, influenced American industry's approach to worker contributions and process innovation. May 8, 1945, arrived with Nazi Germany's unconditional surrender. Victory in Europe Day brought celebrations that swept across America. In aircraft plants throughout the nation, production lines fell silent temporarily as workers absorbed the news. The war in Europe was won. The industrial mobilization that had consumed years of effort had achieved its purpose. For Morrison, the moment brought relief mixed with exhaustion and uncertainty. The immediate pressure was over. The desperate urgency that had driven relentless production had ended. But what came next? Would the innovations and transformations of wartime manufacturing persist into peacetime? Would the democratic empowerment of factory workers survive beyond emergency necessity? The answers emerged gradually over subsequent months. Aircraft production was curtailed dramatically as military orders cancelled. Factories began layoffs, shedding workers who were no longer needed. Women workers faced particular pressure to leave industrial employment, making way for returning servicemen. The social expectation was clear. Wartime employment had been temporary necessity, and traditional gender roles should be restored. Morrison received offers to remain at Boeing in a technical capacity. Her expertise was valued, and the company wanted to retain her knowledge. She declined. The decision surprised many colleagues who had seen her thrive in aircraft manufacturing. Morrison explained that she had spent 4 years in an environment of constant stress, where every decision carried life and death stakes. She needed to step away, to return to something resembling normal life. She reopened her dress shop in downtown Seattle. The work was familiar, comfortable, unconnected to war and death. She created custom garments for wealthy clients, applying the same attention to detail that had served her in aircraft manufacturing, but without the psychological burden. Some former colleagues visited, puzzled that someone with her talents would return to such apparently modest work. Morrison simply smiled and said she had done her part. Frank Kowalski also left Boeing shortly after war's end. He was in his 60s, ready for retirement. His final conversation with Morrison, conducted over coffee in a diner near the plant, reflected on what they had witnessed and experienced. The world had changed, fundamentally, Kowalski observed. Industrial work would never return to the craft tradition he had known. Morrison's innovations represented the future, whether he liked it or not. Morrison acknowledged the transformation, but wondered about its consequences. Mass production had achieved remarkable results under wartime pressure. Would the same approach serve peacetime society as well? She didn't claim to know the answer. They parted as friends, two people from different generations and backgrounds who had contributed to something far larger than themselves. The technical legacy of Morrison's innovations persisted in aviation manufacturing and spread to other industries. The principles she had demonstrated, reversed assembly sequences to improve access, progressive inspection to enhance quality, worker empowerment to unlock expertise, became standard practices in various forms. Textbooks on industrial engineering eventually incorporated concepts that Morrison had developed through intuition and observation rather than formal training. Boeing retained detailed documentation of Morrison's process innovations. Her technical drawings, procedure modifications, and productivity analyses became part of the company's institutional knowledge. Future generations of Boeing engineers studied these materials, often without knowing the name or background of their originator. The knowledge was preserved, even as the person behind it faded from corporate memory. The broader historical recognition came slowly and incompletely. Early histories of World War II aircraft production focused on executives, engineers, and military leaders. The contributions of production workers, particularly women and other non-traditional participants, received minimal attention. Morrison was never mentioned in major histories published during the 1950s and 60s. Only as historians began examining industrial mobilization more comprehensively in later decades did figures like Morrison emerge from obscurity. Researchers studying Boeing's wartime production records encountered her name repeatedly in technical documents and process improvement reports. Oral history projects interviewing former war workers occasionally captured references to the seamstress who had revolutionized wing assembly. A comprehensive study, published in 1996 by aerospace historian Dr. Margaret Stevens, finally gave Morrison's contributions detailed scholarly attention. Stevens documented the wing assembly innovation, the subsequent process improvements, and the broader impact on American aviation production. The research revealed that Morrison's techniques had been adopted not just at Boeing, but throughout the industry, influencing thousands of aircraft across multiple manufacturers. Stevens also contextualized Morrison's achievements within the broader story of women's contributions to wartime production. Morrison was exceptional in the recognition she received during the war itself, but she was representative of thousands of women who brought fresh perspectives and innovative thinking to industrial challenges. The war had opened opportunities, and many women had seized them enthusiastically. The post-war suppression of these achievements, Stevens argued, represented a deliberate effort to restore traditional social structures. Acknowledging that women had excelled in technical manufacturing threatened assumptions about gender capabilities and appropriate roles. By minimizing or forgetting women's contributions, post-war society could more easily insist on their return to domestic spheres. Morrison herself lived to see this historical reassessment. She died in 2003 at age 87, having spent the final decades of her life as a quiet resident of Seattle. Stevens interviewed her extensively in the 1990s, and Morrison's memories provided crucial details about wartime production innovations. She expressed satisfaction that the story was finally being told accurately, but seemed bemused by the attention. The B-17s that Morrison helped build survived her by decades. Museums across America preserve examples of the flying fortress, testaments to the aircraft's significance and the industrial achievement it represented. Visitors can examine the massive wings, run their fingers along rivet lines, and marvel at the complexity of these machines. They rarely know that the assembly processes that built these wings were revolutionized by a former seamstress with fresh eyes and practical insights. The final assessment of Morrison's impact must acknowledge both achievement and limitation. She demonstrably improved B-17 wing assembly efficiency, contributing to increased production that supported Allied victory. Her innovations influenced broader manufacturing practices in aviation and beyond. She exemplified how diverse perspectives and worker empowerment could unlock productivity improvements that traditional hierarchies had missed. Yet, Morrison's story also illustrates the conditional nature of wartime progress. Opportunities opened by emergency necessity closed when emergency ended. The recognition Morrison received during the war evaporated afterward. Her innovations persisted, but her name was forgotten. The potential for continued advancement, for building on wartime gains toward genuine equality, was largely unrealized in the decades following victory. The question Morrison's story raises is whether emergency is necessary for societies to transcend limiting assumptions about human potential. Must crisis force recognition of capabilities that comfortable times refuse to acknowledge? Can the innovations in social organization that emerge from necessity be preserved when necessity passes? Morrison herself seemed to believe that progress, once made, could not be entirely reversed. The women who had proven themselves in factories and shipyards during the war would not forget their capabilities. They would pass different expectations to their daughters. The assumptions about inherent limitations had been challenged too explicitly to be fully restored. The Boeing factories in Seattle, which had produced thousands of B-17s through innovations Morrison pioneered, continued building aircraft for decades. The 747, the 777, the 787, each represented subsequent evolution of aviation manufacturing. The techniques changed, the technologies advanced, but some underlying principles persisted. Good process design mattered. Worker expertise deserved cultivation. Fresh perspectives could identify improvements that experience overlooked. The B-17 itself remained in service for years after war's end. Some aircraft flew civilian roles, converted to cargo or passenger transport. Others served with smaller air forces around the world. A few remained operational into the 21st century, preserved and maintained by organizations dedicated to keeping history flying. These surviving bombers, when they occasionally take to the skies, carry with them the accumulated labor of millions of American workers who built them under unimaginable pressure. One such aircraft, preserved by the Commemorative Air Force and still flown at air shows, bears the name Sentimental Journey. The B-17 was manufactured in 1944 at Boeing's Seattle plant, assembled using processes that Morrison's innovations had transformed. The specific wings on that aircraft were built in approximately 12 hours, rather than the 20 hours that would have been required 3 years earlier. The crews who fly Sentimental Journey at air shows likely don't know about Janet Morrison. They understand the aircraft's mechanical systems, its flight characteristics, its historical significance. They appreciate the craftsmanship that created these machines, but the deeper story, the human creativity and determination that made mass production possible, remains largely invisible. This invisibility represents a broader pattern in how societies remember industrial achievement. We preserve the product's engineering excellence, technological innovation, industrial capacity, but forget the human processes that created them. We celebrate inventors and leaders while overlooking the workers whose insights and labor translated vision into reality. Morrison's innovation, reducing B-17 wing assembly time from 20 hours to 12, then to even less as processes continued improving, represented exactly the kind of contribution that deserved but rarely received historical recognition. It wasn't dramatic invention of new technology. It wasn't brilliant scientific discovery. It was practical insight about workflow organization, the kind of innovation that seems obvious only in retrospect. Yet, this practical insight, multiplied across thousands of aircraft and adopted throughout an industry, contributed measurably to Allied victory. The bombers that struck German industrial targets, that established air superiority over Europe, that supported ground forces advancing across France and into Germany, were built using processes that Morrison helped revolutionize. Her contribution was woven into every rivet, every spar, every completed wing. The final word count of B-17 production, approximately 12,700 aircraft, tells only part of the story. Behind that number stood the labor of hundreds of thousands of workers who mastered new skills, endured brutal schedules, and contributed ideas that transformed manufacturing. Morrison was one among many, exceptional in the recognition she received, but representative of the broader phenomenon. The war demonstrated that human potential, when given opportunity and necessity, could exceed conventional expectations dramatically. Workers without formal credentials could innovate effectively. Women could master technical manufacturing. Industrial democracy, empowering people regardless of background, could unlock productive capacity that hierarchical traditions had suppressed. These lessons, learned through desperate wartime necessity, deserved preservation beyond emergency. The post-war failure to maintain wartime gains represented opportunity lost, potential unrealized. But the knowledge persisted. The proof existed. The precedent had been established. Future generations could look back and see what had been achieved when societies chose empowerment over restriction. Janet Morrison's legacy lives in those who remember that innovation can come from unexpected sources, that fresh perspectives can solve intractable problems, that ordinary people, given extraordinary opportunity, can achieve remarkable things. Her story, finally emerging from historical obscurity, serves as reminder that the heroes who helped win World War II weren't only the generals and pilots, but also the workers who built the weapons that made victory possible. The seamstress who revolutionized bomber wing assembly did more than save manufacturing hours. She demonstrated that expertise comes in many forms, that conventional wisdom deserves challenging, that transformation often requires seeing familiar problems through unfamiliar eyes. These lessons, learned on factory floors under wartime pressure, remain relevant whenever societies face challenges that demand innovation. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.